In this video, we're going to discuss a concept in chemistry known as entropy. And entropy is, for reasons that are not important or clear, is abbreviated with the letter S. And as an introduction to entropy, we're going to use an analogy with playing cards. I got this from one of my college professors, John Hutchinson at Rice. So much appreciation to him for this one. So let's imagine we have 3 cards and we're asked how many different orders can we place it in? Well, we can have just the order we have shown here, 1, 2, 3. So that's one possible order. We could also have 1, 3, 2. That's another one. We could have 2, 1, 3. 2, 3, 1. Or we could have the 3 in front, 3, 1, 2, or 3, 2, 1. Now, in addition to that, we're going to define we're going to call all of these a state. So the particular order is going to be a state. So there are 6 possible states when we have 3 cards, and we're going to define only this one here as the ordered state. All right, so we have 6 states, one of which is ordered, and we're going to define the other 3 as disordered. So the next question is, well, what if we have more cards? What if you have 1, 2, 3, and 4? Well, now there's many more states that you can generate. In fact, there are going to be 24 different states you can generate from these 4 cards, only one of which is ordered. Again, the 1, 2, 3, 4. If you have 5 cards, it turns out there's 120 possible arrangements, and only the 1, 2, 3, 4, 5 is ordered. So what happens is that the likelihood is so much higher. So here, let's make a list. So if you have 3 cards, there are 6 states, and only one of them is ordered. If you have 4 cards, there are 24 states, only one of which is ordered. If you have 5 cards, there are 120 states, only one of which is ordered. And you can go on and on like this. The formula for this is actually the number factorial, so 5 times 4 times 3 times 2 times 1. And it turns out that most of the time, we are going to find that there are far more disordered states than there are ordered states. So there are far more disordered states than ordered states. And so just by chance, if you observe a system, it's most likely that you're going to observe a disordered state. Particularly for the fact that this is with 5 cards. Imagine if you have a mole of gas, 6.0 times 10 to the 23rd. Imagine how many states or orders you could put the atoms in to obtain a different state. So it's just going to be far more likely that we're going to find a disordered state just by chance than to find an ordered state. In order to deal with this fact, we're going to define a function called entropy. And the exact definition of it is not that important, but we're going to define the entropy as a measure of the number of states in a system. In a chemical system, we're going to find the states as the total number of positions and speeds of the particles all right, and the more states there are, the higher this value of entropy is going to be. Now, how can we predict that a particular chemical system is going to have a higher or lower entropy? Well, we're going to do that based on whether or not we think that at the atomic level, the system is going to have a large number of states, a large number of possible positions, a large number of possible speeds. And so as an example, I've drawn water in its 3 different states as they're normally observed, solid, liquid, gas. And so in the solid state, we have a nice ordered lattice of water molecules. This is a kind of crummy drawing of the lattice, but whatever. So the water molecules are trapped in one position. In the liquid, they're a little farther apart, not much, but a little bit, enough to allow them to move past one another. So I've drawn arrows to indicate possible movements and possible speeds for them. And then in the gaseous state, the water molecules are farthest apart and they have the greatest possible speed. Some of them can be going quite fast, some of them can be going quite a bit slower. So we would expect that the gas would have the most possible states, and therefore that's going to equate to the highest value of entropy. Okay, so in terms of, if we're ranking these in terms of their entropy, the gas will have the greatest entropy. In fact, the gas will have quite a lot more entropy, so we would use the much greater than symbol than the entropy of the liquid state, and that would have more entropy still than that would be a greater entropy value than the entropy value for water in the solid state, excuse me. So we're always going to find this, that gas is always going to be much greater in entropy than liquid. It's always going to be greater in entropy than solid. And we're going to use this to predict the change in S for a process. So for example, if we melted ice from solid to liquid, that would be an increase in entropy. We're going to call that a positive delta S, change in entropy. If we go from gas to liquid, if condensation, that's going to be a negative delta S because the S value is going to decrease. We're going to use this in a number of situations to predict, without having to do any calculations, what the sign of the change in S, the delta S, is going to be.